Right now, somewhere in a massive, windowless warehouse, the computers training the next generation of artificial intelligence are running so hot that they're literally on the verge of melting their own silicon.
Yeah, it is a very real physical limit we are hitting.
It's crazy to think about because we all walk around with this, I don't know, this illusion of weightlessness when it comes to technology. We literally call it the cloud, right?
Which sounds so light and airy.
Exactly. We stream petabytes of data, we query these massive language models, we run complex enterprise workloads, and to us, sitting at our laptops, it all feels light, fluffy, almost magical.
But the physical reality behind the curtain is, well, it is the exact opposite of weightless.
Yes. As of today, August 10th, 2026, the reality of the cloud is that it is dense, it is incredibly power hungry, and it produces this physical byproduct that is actively threatening to bottleneck the entire global tech industry.
You are talking about the heat.
The massive, unmanageable heat. So today, for you listening, we are going on a deep dive into why the internet is quietly having to abandon air cooling entirely, and why the future of AI depends basically entirely on plumbing.
It really is the ultimate paradox of the digital age, you know?
How do you mean?
Well, we are dealing with these invisible weights and measures, neural network weights, parameters, floating point operations. But we remain absolutely bound by the very tangible, very stubborn laws of thermodynamics.
Right? You can't code your way out of physics.
Exactly. Highlighting heat as the ultimate bottleneck is really the only way to view the current landscape. This has escalated way beyond just a standard engineering hurdle.
It's an existential threat to the industry.
It really is. The thermal wall is the central defining challenge of modern computing infrastructure right now.
And that thermal wall is exactly our mission for this deep dive today. We are tearing into a fascinating white paper from Supermicro, and it details their DLC-2 architecture.
Which stands for direct-to-chip liquid cooling, for those wondering.
Right, thank you. So we are going to take you behind the curtain into this hidden, highly industrialized world today, because unless you are literally a data center architect, you probably never think about the sheer physical infrastructure required to keep the global intelligence grid from, well, catching fire.
It's something people take completely for granted.
Totally. Okay, let's unpack this because my immediate instinct, and I think the instinct of anyone who has ever, built a PC or even just looked at a server rack, is to ask why we can't just brute force this problem.
The brute force method.
Right. Like if the chips are getting hotter, why not just build bigger, faster fans? Why not just blast a literal hurricane of cold air through the chassis and call it a day?
Well, that brute force approach is exactly what the industry has relied on for, the better part of 3 decades.
And it worked fine for a long time, right?
It did. For a long time, it worked perfectly. You just increased the RPM of the fans, you expanded the surface area of the metal heat sinks, and you just pushed more chilled air through the room.
Simple enough. So why stop now?
Because we have fundamentally reached the end of the runway for air cooling. The physics simply no longer support it.
Like it literally just can't keep up.
Exactly. To understand the mechanism of why air has failed us here, we really have to look at something called TDP, or thermal design power.
Okay, right. TDP is essentially, it's the maximum amount of heat generated by a chip under a heavy workload, right?
Yes, exactly.
And the system's cooling apparatus has to be able to dissipate that specific amount of heat to prevent the chip from thermal throttling or just dying.
Correct. And for the new generation of processors, particularly the heavy-duty GPUs that are driving these AI workloads, those TDPs are rising on a curve that is almost vertical right now.
Wow, really?
Oh, yeah. We are seeing thermal output numbers today that would have been laughed out of engineering meetings just 5 years ago.
Because they would have seemed impossibly high.
Exactly. The core issue is that heat generation is accelerating at a pace that entirely outstrips the physical limitations of forced air convection.
Okay, I really want to drill into the why there, because on the surface, we hear all the time in the news that chips are getting more and more efficient.
Right. The node shrinks.
Yeah, we are shrinking transistor nodes down to, just a handful of nanometers now. So if the underlying architecture is getting so much more efficient, why is the absolute heat output just skyrocketing?
It really comes down to the breakdown of something called Dennard scaling. And you have to combine that with the massive parallelization required by AI.
Okay, walk me through that. What is Dennard scaling?
Well, for a long time, as transistors got smaller, their power density stayed roughly constant. So you could pack way more of them into a chip, and they would run faster, but they wouldn't necessarily use exponentially more power.
Which sounds like a great deal.
It was. But that rule broke down over a decade ago.
Hmm.
Now we are packing tens of billions of transistors onto a single tiny piece of silicon.
And they are all drawing power.
Exactly. And to process modern AI workloads where you are doing, billions of matrix multiplications simultaneously, you have to light up vast sections of that silicon all at once.
Oh, I see. So even though an individual calculation takes less energy than it did, say, 10 years ago, we are performing millions of times more calculations concurrently.
Precisely. You are cramming an unprecedented amount of electrical current into a highly, highly condensed physical area.
And almost all of that electrical energy eventually degrades into heat, right?
Yes, it is an unavoidable byproduct. It comes from the electrical resistance in the microscopic copper traces and the actual physical switching of the transistors.
Right, just basic friction at a tiny scale.
Exactly. Now, returning to your question about simply building bigger fans,
Yeah.
the fundamental problem there is that air is an insulator.
Wait, air is an insulator?
Yes. By its very chemical nature, air is a terrible conductor of heat. Its thermal capacity and its thermal conductivity are incredibly low compared to liquids.
Which means air doesn't actually want to absorb the heat off the chip. You really have to force it to do the work.
You have to force it violently. If you just push more and more air through a standard 4U server chassis, you aren't efficiently pulling the heat off that dense silicon anymore.
It just kind of blows past it.
Right, the air just skims over the heat sinks. So to get enough actual heat transfer, you have to push the air so fast that you create these massive high-velocity wind tunnels inside the servers.
Which sounds incredibly loud and aggressive.
It is. And spinning those tiny fans at 15,000 or even 20,000 RPM, it consumes a terrifying amount of electricity.
Which kind of defeats the whole purpose, doesn't it? You end up spending a massive percentage of your data center's entire power budget just spinning these plastic fan blades rather than actually crunching data.
That is exactly the trap. It becomes a negative feedback loop. The fans use more power, which generates more heat in the system's power delivery components, which then requires even more cooling.
That sounds like a complete nightmare for an engineer.
It is unsustainable. Liquid, on the other hand, is a conductor. Depending on the specific fluid dynamics, liquid water can carry thousands of times more heat energy per unit of volume than air.
Thousands of times more. That's a massive difference.
It really is. The basic cycle of liquid cooling is physically very elegant. You take a supply liquid, often just ambient water, and flow it directly over the hot components using a cold plate.
And it just soaks the heat right up.
Exactly. The liquid absorbs that thermal energy via direct conduction, which is vastly more efficient than the convection you get with air.
Right.
It then travels in a closed loop out to an external heat exchanger, releases the thermal energy, drops back to its base temperature, and returns to the server to do it again.
Okay, I have an analogy for this. It is basically the difference between trying to cool down a scorching hot cast iron frying pan by, blowing on it with your mouth versus just tossing it straight into a sink full of water.
That is a perfect analogy, actually.
Because blowing on the pan is going to take literally forever, and you are going to exhaust yourself pushing all that air. But the water transfers the energy almost instantaneously because of its density. You get that big hiss of steam.
Right. The phase state of the medium changes everything about the interaction. The thermal mass of liquid allows it to act like a sponge for heat, whereas air acts like a very stubborn, very inefficient sieve.
It just doesn't want to hold the heat.
Exactly. And because of this, we are currently witnessing one of the most significant architectural shifts in the entire history of internet infrastructure.
Moving from wind to water.
The entire backbone of the global compute grid is moving from wind to water, yes.
Okay, so if liquid is the undeniable winner when it comes to just the raw physics of it all, how do we actually quantify that on an industrial scale? Because we aren't talking about water cooling a custom gaming PC in a teenager's bedroom here.
No, absolutely not.
Supermicro is designing architectures for warehouse-scale computing, where you have tens of thousands of these nodes networked together. So how do they measure the impact?
Well, the scale requires an entirely new framework of measurement, and the Supermicro white paper provides a blueprint for this transition by laying out 4 critical metrics.
The 4 UEs, right.
Yes, the industry categorizes them as the 4 UEs. If you are an architect designing a new AI factory, or even retrofitting a legacy data center, these are the fundamental laws you have to abide by now.
Okay, I want to tackle these one by one. The first 2 directly address the physical footprint and the electrical draw, right? PUE and SUE.
Correct. power usage effectiveness, and space usage effectiveness.
Okay, I want to push back on the power aspect first with PUE, because if we swap out thousands of tiny fans for massive industrial liquid pumps, I mean, pumps require a ton of electricity too, right?
They absolutely do.
Pushing thousands of gallons of water through miles of microscopic channels in these cold plates has to take serious mechanical force. So are we actually saving power, or are we just shifting the data center's electricity bill from fan motors over to pump motors?
That is a highly relevant engineering concern, and it goes directly to the heart of what PUE actually measures.
Okay, break down PUE for us.
PUE is the gold standard metric for data center energy efficiency. It is a simple ratio. You calculate the total amount of power entering the entire data center facility, and you divide it by the power actually consumed by the IT equipment.
So the IT equipment means the servers, the storage, the networking switches, the stuff actually doing the math.
Exactly.
So a theoretical perfect score would be 1.0, right? Meaning every single watt entering the building goes directly into a processor, and literally 0 watts go into overhead, like cooling or lights.
Which is physically impossible, of course, because you always need lights, security systems, and some baseline environmental control. But 1.0 provides our baseline ideal.
Got it. So what does a normal air-cooled data center score?
In the Supermicro model, when analyzing legacy infrastructure, a standard air-cooled data center has an assumed PUE of about 1.5.
Okay, so let me do the math there. That means for every megawatt of power you dedicate to actually running your AI models, you are paying for an additional half a megawatt just to keep the building's lights on and the air conditioners blowing.
Specifically, the massive CREC units, the computer room air conditioning units.
Yes, half a megawatt of pure overhead. That is exactly what we want to avoid. That is a massive penalty just for doing business.
Is a huge operational drag. But when you move to the DLC-2 liquid cooling architecture, that PUE plummets from 1.5 down to 1.1.
Wow, 1.1. That implies an incredibly tight system, almost no overhead at all.
It is remarkably efficient.
But let's go back to my pump versus fan debate for a second.
Yeah.
How does the PUE drop so drastically if we are still running heavy mechanical water pumps?
Because the sheer efficiency of liquid thermal transfer vastly outweighs the mechanical cost of pumping it.
Really? It's that much of a difference?
Oh, absolutely. Moving a small, dense volume of water requires significantly less energy than moving an absolutely massive, highly volatile volume of air.
Okay, that makes sense. Air is just bulky.
Exactly. Fans have to constantly overcome the aerodynamic impedance of a densely packed server chassis. It's like trying to blow air through a brick wall.
Right.
But pumps operate in a closed, pressurized hydraulic loop. Once the fluid is moving, maintaining that flow rate across the cold plates is highly energy efficient compared to trying to force air through tiny metallic fins.
Because the water naturally wants to keep flowing once the pressure is equalized.
Exactly. The white paper actually breaks down the math on this explicitly.
What's the calculation they use?
They compare the IT power for a 4U liquid-cooled system multiplied by that 1.1 PUE against a 10U air-cooled system multiplied by the old 1.5 PUE.
And what does that ratio come out to?
The result is a 60% power consumption ratio.
Meaning a 40% total power savings just by switching to liquid.
Exactly. And if you are operating a 100 megawatt facility, which is increasingly common for large language model training right now, saving 40% on your total power draw is not just an operational win.
It's massive. That's 40 megawatts.
Right. And honestly, it might be the only way the local utility grid actually allows you to build a facility in the first place. Power grids are heavily constrained right now.
That's a great point. If you ask a city for 150 megawatts for an air-cooled setup, they might say no. But 110 megawatts for liquid, they might approve it.
Exactly. A 1.1 PUE means that essentially all the massive electrical contracts you are signing are actually yielding compute cycles rather than just generating artificial wind in a warehouse.
I love that phrasing, generating artificial wind. That really puts it in perspective. The density of the liquid medium just outright wins over the mechanical cost of moving it.
It absolutely does.
Which brings us perfectly to the second UE metric, SUE, or space usage effectiveness. The source notes a massive physical footprint reduction here.
Right, the density improvements.
They say we go from a 10U air-cooled system down to a 4U liquid-cooled system, and SUE measures the liquid-cooled rack density against the old air-cooled rack density.
The physical volume reduction there is remarkable. You are taking a piece of hardware and shrinking its physical casing by 60%.
And just for you listening, if you aren't familiar with server racks, a U is just a standard unit of vertical measurement in a rack. So going from 10 units tall to 4 units tall is a huge shrinking of the box,
It frees up over half the rack space.
which means we can pack 60% more computing power into the exact same vertical space in a warehouse.
Yes.
But here is where my internal alarm bells go off again. I try to picture this in my head. If we are cramming 60% more computing power, which means 60% more hot silicon, drawing massive amounts of electrical current into the exact same physical warehouse footprint, aren't we just building a denser, more dangerous inferno?
It sounds like it, doesn't it?
Yeah. If you walk into a server room that is packed twice as tight with hardware and that hardware is running hotter than any previous generation in history, how is that room even habitable for a human being? How does the building not spontaneously combust?
It is a totally valid fear, and it is based on decades of our own conditioning. We're used to data centers feeling like the exhaust of a jet engine.
Right. You walk in, and it's a hurricane of heat.
But the shift to liquid cooling completely isolates the heat from the ambient environment of the room.
How so?
Well, in a legacy air-cooled facility, the servers act like massive space heaters. They ingest cold air from the room, they run it over the hot components, and they basically vomit that scorching hot air right back out into the aisle.
Which is why they have to build those classic hot aisle, cold aisle containment systems, right? It's like a constant war of air pressure in the room.
Exactly. It is a constant battle against the ambient air. But with direct-to-chip liquid cooling, that war ends entirely.
Because the heat is trapped in the water.
Yes, the heat is trapped inside the fluid within a closed, hermetically sealed loop. The thermal energy is conducted from the silicon directly into the water, and that hot water is piped directly out of the server, out of the rack, and immediately out of the building.
Oh, wow. So the heat effectively bypasses the ambient air of the server room entirely.
Exactly. It never touches the air you were breathing.
So you could walk into a facility running tens of thousands of liquid-cooled GPUs drawing megawatts of power, and the room temperature could just feel like a normal, comfortable office building.
In many cases, yes. The ambient air is no longer the primary thermal transport mechanism.
That is wild to think about.
Now, you might still have some residual heat from, say, networking cables or minor chassis radiation, but the overwhelming majority of the thermal load is locked securely in the plumbing.
So you aren't creating a denser inferno at all.
Not at all. You are creating a highly organized thermal highway that safely escorts the heat out of the building without it ever lingering in the room.
So SUE doesn't just mean you save real estate or warehouse space. It means you fundamentally alter the physical experience of being inside the data center.
It completely changes the working environment, yes.
Okay, that brings me to my next major point of skepticism, and it's something the white paper actually addresses directly with the third metric. We are talking about using a massive continuous flow of water to safely escort this heat away. In a global climate right now where water scarcity is a top-tier environmental and political issue, shifting the internet's primary cooling mechanism over to water sounds, frankly, like an ecological disaster.
It is a very common concern.
Like, how can we possibly justify evaporating millions of gallons of fresh water just to train a new AI model to write emails for us?
You have hit on one of the most critical and honestly most pervasive misconceptions in the entire tech industry.
Really? A misconception?
Yes. The baseline assumption everyone makes is that liquid cooling consumes more water than air cooling. Sounds logical, right?
Yeah, air cooling uses air. Liquid cooling uses water. It seems pretty straightforward.
But this brings us to WUE, or water usage effectiveness. And the reality of the physics tells the exact opposite story.
Wait, what do you mean?
Liquid-cooled data centers actually use substantially less water overall than traditional air-cooled facilities.
Wait, stop. That sounds like corporate spin. How can a water-cooled system use less water than a system that literally relies on fans?
To understand this, we have to pull back the lens and look at how a massive air-cooled data center actually produces that cold air in the first place.
Okay, sure.
It doesn't just open a window and blow outside air into the server room. That outside air is often way too hot, too humid, or full of dust and pollutants.
Right. You need a pristine, chilled environment.
Exactly. So the facility has to actively refrigerate the air using massive industrial HVAC chillers. And at that scale, the most efficient way to reject heat from those chillers is through evaporative cooling towers.
Evaporative cooling towers, so they are using water to chill the air.
Yes. The data center is essentially sweating to cool itself down. It evaporates water into the atmosphere, utilizing the latent heat of vaporization to chill a separate water loop, which then chills the air that finally gets blown into the server room.
Oh my God, I never thought about it like that. So the air-cooled system is secretly just a massive water consumer behind the scenes.
Exactly. And evaporative cooling consumes a staggering, almost incomprehensible volume of water. We are talking about millions of gallons per month for a single large facility.
Millions of gallons just turned to vapor.
Literally turned into vapor and lost to the local atmosphere, strictly to condition the air inside the building. So an air-cooled data center relies heavily on water for its HVAC infrastructure, in addition to its massive electrical draw.
Okay, my mind is a little blown, but how does Supermicro's DLC-2 avoid doing the exact same thing? If the water inside the server absorbs the heat, it still has to reject that heat somewhere outside the building, right?
Yes, it does.
So why doesn't the liquid-cooled facility also have to evaporate millions of gallons of water to chill its own water loop?
Because of the temperature differentials involved,
Yeah.
which the white paper highlights as a major architectural advantage. DLC-2 uses warm water.
Warm water?
Yes, it uses supply liquid at ambient temperatures rather than relying on mechanically pre-chilled refrigerated water.
I want to make sure I understand the mechanism here. Because we are applying the water directly to the incredibly hot silicon via a cold plate, the water itself doesn't actually need to be ice cold.
Exactly.
It just needs to be cooler than the chip itself.
That is the absolute crux of the engineering right there. If you are trying to cool a room full of ambient air, you need your chiller water to be very, very cold to affect the room temperature.
Right.
But if you are directly contacting a processor die that is operating at 90 degrees Celsius, a water supply that is sitting at 35 or even 45 degrees Celsius is deeply, effectively cold relative to that silicon.
Because 45 is so much lower than 90.
Exactly. Because of the direct conduction, the heat transfer happens rapidly, even without running the water through a refrigeration cycle.
I see. It's kind of like the difference between trying to cool down an entire massive warehouse by blasting the air conditioning versus just wearing a localized liquid-cooled astronaut suit.
That is a very apt comparison.
The traditional data center evaporates a literal lake to chill the ambient air for the whole room. But the direct-to-chip system just runs a closed loop of ambient water, meaning you completely bypass the need for those massive water-evaporating HVAC chillers.
You eliminate the refrigeration cycle almost entirely. You rely heavily on dry cooling towers or Sibyl heat exchangers that reject the heat directly into the outside air without needing to evaporate water to force the temperature down artificially.
Wow. And what is the result of that in the Supermicro metrics?
The result is that the DLC-2 architecture uses 40% less water overall compared to a traditional air-cooled facility.
That completely flips the script on the environmental argument. You are not only saving power, but you are actively conserving massive amounts of municipal water by moving to a liquid medium.
It is a double victory for sustainability, yes.
And that efficiency cascade leads directly into the final metric. The fourth UE, which is UE, or money usage effectiveness, though I think the industry universally refers to it as TCO, right? Total cost of ownership.
Yes, TCO. And TCO is the metric that ultimately determines whether these AI architectures are actually financially viable in the real world.
Right, because none of this matters if it bankrupts the company building it.
Exactly. The economics of large-scale computing are incredibly unforgiving. If a technology doesn't map to a lower total cost over its entire life cycle, it just remains a cool science experiment in a lab.
But the math here seems almost inevitable now that you've laid it out. If your PUE drops to 1.1, giving you a 40% power reduction,
Right.
and your SUE allows a 60% footprint reduction, meaning you can buy less land and build a physically smaller warehouse,
Exactly.
and your WUE cuts your municipal water utility bill by 40%, all of those operational and capital expenditures just collapse inward.
They compound on each other. And the white paper models this out to a 20% lower TCO over time, a 20% reduction in total cost of ownership. Let's put that in perspective. What does 20% mean for a hyperscale facility? On a billion-dollar data center deployment, which is becoming the norm, a 20% reduction is a structural shift in the business model. It means $200 million in capital that can be redirected.
$200 million saved just by changing how you move heat.
Yes, you can redirect that into acquiring more compute nodes, hiring more top-tier researchers, or aggressively undercutting your competitors on pricing for AI API access.
It's a brutal economic advantage.
It proves that direct-to-chip cooling isn't just an environmental necessity anymore. It is a fundamental business imperative. The companies operating at a 1.5 PUE with air cooling simply will not be able to compete on price with facilities running a DLC-2 liquid architecture.
So what does this all mean? We have established the macro reality. The four UEs paint a picture of undeniable supremacy for liquid cooling. 40% less power, 60% less space, 40% less water, and 20% less money.
It is a clean sweep across all metrics.
But I'm, inherently skeptical of magic bullets.
Yeah.
To achieve numbers like this, the physical engineering under the hood must be completely flawless.
The engineering is quite remarkable, yes.
I want to break down the actual DLC-2 blueprint now. How does Supermicro physically pull this off at the rack level? Let's start with this inlet temperature metric because it completely bends my mind. The systems can use supply water up to 45 degrees Celsius.
The high inlet temperature capability is perhaps the most important engineering achievement in the entire architecture.
Why is that?
Because it is the central linchpin that unlocks the water savings, the WE savings we just discussed.
But wait, hold on. 45 degrees Celsius is roughly 113 degrees Fahrenheit. That is literal hot tub water.
It is quite warm to the touch, yes.
If I have a piece of fragile billion-dollar silicon operating near its thermal limit, and I pump 113-degree water over it, I'm struggling to understand how that doesn't just bake the chip alive. Doesn't the heat sink medium need to be aggressively cold to draw heat away fast enough?
It is deeply counterintuitive until you frame it exclusively through the lens of thermodynamics.
Okay, put my thermodynamics glasses on.
Heat transfer is not about absolute temperatures. It is entirely governed by the temperature differential between two objects, which is known in physics as delta T.
Delta T meaning the difference in temperature.
Exactly. Heat always, inevitably, flows from a higher energy state to a lower energy state. The speed of that flow is dictated by the delta T and the thermal conductivity of the materials involved.
So if the GPU is screaming along at 90 degrees Celsius and the water is at 45 degrees Celsius, there is still a massive 45-degree delta T.
Correct. And because water is roughly 24 times more thermally conductive than air and has a volumetric heat capacity over 3,000 times greater than air.
3,000 times.
Yes, because of those properties, that 45-degree water acts as an absolute thermal vacuum for the 90-degree energy on the chip.
This just sucks it right out.
The water molecules rapidly absorb the vibrational kinetic energy from the silicon's heat spreader. The fluid simply doesn't need to be 10 degrees Celsius to do the job. 45 degrees is more than sufficient to prevent the kit from exceeding its maximum junction temperature.
The density of the liquid completely compensates for the relatively high starting temperature. That is brilliant.
It is elegant physics.
And because you are legally allowed, so to speak, by the laws of physics to use 45-degree water, you don't need compressors and refrigerants to chill the water loop.
Exactly. You just run it outside, let the ambient air cool it down, and cycle it back. Even in the middle of a desert summer, the outside air is almost always cooler than 45 degrees Celsius, which is 113 Fahrenheit.
Right. So you bypass the mechanical refrigeration cycle entirely, saving enormous amounts of power and water.
That is the secret to the efficiency.
Okay, so once the fluid absorbs that heat from the chip, it has to be managed and distributed, which brings us to the next physical component in the blueprint. The in-rack CDUs, or coolant distribution units.
The CDU is the beating mechanical heart of the entire liquid loop.
The white paper states they have drastically increased the capacity of these CDUs. They are now capable of removing 250 kilowatts of heat per rack.
Yes, that is a 150% increase over the older 100 kilowatt CDUs.
So where does this CDU actually sit? Is it in a back room somewhere?
No, it sits right there inside the server rack itself.
Yeah.
It takes up a few U space. It contains the primary pumps, the fluid reservoirs, the microfiltration systems, and a liquid-to-liquid heat exchanger.
A liquid-to-liquid heat exchanger? What does that do?
It acts as a bridge. It interfaces the pristine internal server fluid loop with the facility's external rugged water loop that goes outside to the towers.
Ah, so the water touching the chips isn't the exact same water going outside.
Right, they are isolated loops transferring heat across a plate inside the CDU, and moving 250 kilowatts of thermal energy across that bridge is an industrial-scale task.
I really want to contextualize 250 kilowatts because for most people, it is just an abstract number.
How would you visualize it?
Well, an average home space heater, the kind you plug into a wall outlet that immediately warms up an entire living room, that puts out about 1.5 kilowatts of heat.
Okay, that's a good baseline.
So if we do the math, a single server rack equipped with this new CDU is generating and safely managing the thermal equivalent of roughly 160 space heaters running at absolute maximum blast.
That is a staggering visual.
And all 160 of those space heaters are confined within a physical space, roughly the footprint of a kitchen refrigerator.
It is a terrifying concentration of thermal energy.
Yeah.
Honestly, without the localized fluid pressure and massive flow rates generated by that 250 kilowatt CDU, the internal silicon would melt into slag within seconds.
Within seconds. It wouldn't even last a minute.
Not at that density. The CDU is what ensures that the volumetric flow rate of the coolant across all the cold plates is perfectly calibrated to the dynamic thermal load of the rack at any given millisecond.
And how exactly does it capture all 160 space heaters worth of energy so efficiently? The white paper details something called cold plate coverage.
This is a critical evolution in the hardware design.
The paper states that the liquid plates now cover the CPUs, the GPUs, the PCIe switches, the DIMM memory modules, the voltage regulators, and even the power supplies. They claim this captures up to 98% of the heat generated by the system.
Capturing 98% of the heat directly into the liquid represents a vital evolutionary leap in system design.
How was it done before this?
Well, in the early experimental days of liquid cooling in data centers, architects would just slap a water block on the CPU, because it was obviously the hottest component, and they would leave traditional fans in the chassis to blow air over everything else.
It's like a hybrid approach.
Exactly. But in the modern era of large language models, the auxiliary components are running incredibly hot too.
Right, because if you have a GPU doing massive matrix math, it requires an immense amount of data, which means the memory modules, the DIMMs, are working overtime.
Yes, memory generates significant heat now. And to deliver the hundreds of amps of electrical current to the processor, the voltage regulators, the VRMs, are experiencing massive resistive heating.
So if you only liquid cool the GPU, the VRMs and the memory will eventually overheat and bottleneck the entire system anyway.
Exactly. A chain is only as strong as its weakest thermal link. So Supermicro's architecture team engineers these custom microchannel cold plates that make direct thermal contact with virtually every single heat-generating surface on the motherboard.
It just blankets the whole board.
By routing the coolant through this highly intricate, highly parallel plumbing network inside the chassis, they intercept 98% of the thermal energy before it ever has a chance to radiate into the ambient air of the server box.
It is full systemic containment. You aren't just putting a Band-Aid on the hottest chip anymore. You are wrapping the entire nervous system in a thermal vacuum.
That is exactly what allows them to remove the high-speed fans.
Which explains so much. But once that 98% of heat is captured by the CDU and sent out of the building on the facility loop, how is it ultimately rejected to the outside world? The source mentions something called hybrid cooling towers.
The rejection mechanism is crucial, especially for global deployments. A data center built in, say, Iceland, faces very, very different thermodynamic realities than one built in Arizona.
Obviously.
So the hybrid cooling towers integrate both standard evaporative mechanisms and dry radiator-style mechanisms into a single unified structure.
Oh, so it can adapt to the seasonal climate on the fly.
Precisely. If you are in a location with severe temperature swings, say 100 degrees Fahrenheit in August, but well below freezing in January.
Like a lot of the Midwest U.S., for example.
Right. The control logic of the facility adapts automatically. During the extreme heat of summer, when the ambient air might exceed that 45 degrees Celsius inlet threshold, the tower can activate an evaporative assist mode.
Where it sprays water to cool it down.
Yes, it sprays a fine mist to drop the temperature via latent heat, just temporarily. But the moment the weather cools down, or during the entire winter season, it switches to a purely dry cooling mode.
And what does that do?
It just runs the hot fluid through a massive radiator and lets the freezing winter air pull the heat away natively using strictly zero water.
Maximizing efficiency in real time based on the local meteorology. That is just brilliant.
It optimizes the WUE dynamically.
Okay, so we have this incredible infrastructure established, 45-degree water pumped by a massive 250 kilowatt CDU, capturing 98% of the heat across the entire motherboard and rejecting it through these climate-aware hybrid towers.
A masterpiece of modern plumbing.
But this intricate, massive thermal architecture only exists because the computing hardware absolutely demands it.
Yes, the tail does not wag the dog here. The chips dictate the cooling.
Exactly. The source details one of the primary drivers of this heat, and I really want to spend some time looking at it. Let's meet the beast that sits inside these racks. The SYS 422GS NBRT LCC server.
This is the silicon sledgehammer. This is the physical realization of the AI boom, housed within that dense 4U form factor we discussed earlier when looking at SUE.
To give some context on the specs for our listeners, this single 4U chassis contains two Intel Xeon 6 series processors acting as the host CPUs, which the paper notes can draw up to 500 watts each.
Which is incredibly hot for a CPU.
Right. But the absolute showstopper, the real reason this machine exists, is the graphics processing. It houses an NVIDIA HGX baseboard populated with 8 B200 GPUs.
8 of them in one box.
And the white paper explicitly states these GPUs can draw up to 1,000 watts each.
The power delivery requirements for this server are staggering. 1,000 watts for a single discrete piece of silicon is a threshold that completely alters the fundamental electrical engineering of the motherboard.
Let's really pause and think about what 1,000 watts means at the microscopic chip level, because a high-end consumer microwave uses about 1,000 watts to rapidly boil a cup of water in your kitchen.
Yes, 1,000 watts is immense localized energy.
We essentially have 8 microwaves running at absolute continuous full blast alongside 2 high-end 500-watt processors packed inside a metal box roughly the size of a carry-on suitcase.
And we also have to consider the voltage here, not just the wattage.
What do you mean?
Modern processors operate at extremely low voltages, often around 1 volt or even less. To deliver 1,000 watts of power at 1 volt, the power delivery network has to push 1,000 amps of electrical current into that single GPU socket.
1,000 amps? That sounds lethal.
It is an absurd amount of current. That requires massive, incredibly thick copper traces just to prevent the motherboard itself from melting due to resistive heating before the power even reaches the processor.
Oh, wow. So the board itself is fighting to not catch fire just from delivering the power.
Exactly. The engineering required to manage the localized joule heating from 1,000 amps is arguably just as complex as the logic gates on the chip itself.
That is wild.
When you combine 8 of these B200 GPUs, plus the dual Xeon 6 processors, plus the high bandwidth memory and the networking interfaces, a single 4U server is drawing near 10 kilowatts of power continuously.
And as we established earlier, almost all 10 kilowatts of that electrical energy degrades directly into thermal energy.
It is a 10 kilowatt heater.
If you attempted to cool 8,000-watt GPUs with traditional forced air, what would actually happen?
It would be an acoustic and thermal catastrophe. The fans required to push enough CFM, which is cubic feet per minute of air, over those heat sinks, would have to spin at RPMs approaching literal jet turbines.
Which would be deafening.
Beyond deafening. The acoustic vibration alone from fans spinning that fast could cause physical microfractures in the microscopic soldered joints of the motherboard over time.
You're kidding. The sound would break the computer.
Yes, acoustic vibration is a known failure vector in high-density environments. Furthermore, the air simply wouldn't have the thermal capacity to pull the heat off the die fast enough anyway.
So it would just fail.
The chips would hit their thermal limits in seconds and engage extreme thermal throttling. They would forcefully drop their clock speeds to avoid self-destruction.
So you would pay millions of dollars for state-of-the-art AI performance, and you would receive a fraction of the actual compute power because the hardware is basically choking on its own exhaust.
Precisely. You would be stranding your own compute investment.
This brings us to a fascinating human element detailed in the white paper, actually. By utilizing the 98% liquid capture, Supermicro has drastically reduced the need for those high-speed chassis fans we just talked about.
Because the liquid is doing all the heavy lifting.
Right. And the paper highlights up to 25 decibels of noise reduction, dropping the acoustic output of the server to as low as 50 decibels.
The acoustic environment of a data center is an incredibly overlooked aspect of infrastructure engineering. Most people never think about it.
Because they've never been inside one.
Right. Sound is essentially pressure waves, and 25 decibels of reduction is not a linear decrease. Decibels operate on a logarithmic scale.
Meaning a 25 decibel drop represents a massive exponential reduction in actual acoustic energy hitting your eardrums.
Exactly. Traditional high-density air-cooled data centers are fundamentally hostile environments for human beings. They routinely operate at 80 to 90 decibels.
90 decibels, that is like...
It is akin to standing next to a busy highway or someone operating a jackhammer. It is a severe occupational hazard.
I can't imagine working an 8-hour shift in that.
You don't, without protection. Facility technicians, network engineers, and hardware specialists are required by law to wear heavy, industrial hearing protection just to walk down an aisle to replace a single faulty cable.
And you can't even talk to each other.
No, communication is entirely nonverbal in those rooms. You have to use hand signals or literally text messages while standing right next to someone.
But the white paper claims 50 decibels for the liquid-cooled system. 50 decibels is the volume of a quiet office conversation or like a modern refrigerator humming in a kitchen.
It is dramatically quieter.
You are telling me a technician could stand directly next to a rack drawing hundreds of kilowatts of power, processing the most advanced large language models on the planet, and they could just have a normal, unprotected conversation with a colleague.
Yes. It transforms the physical reality of the data center from a deafening, high-velocity industrial wind tunnel into a relatively serene, highly efficient computing laboratory.
That is just incredible for the quality of life of the workers.
Furthermore, the SYS-422GS design features a front I/O architecture.
Front I/O meaning input-output.
Yes, meaning all the networking cables and interfaces are accessible directly from the cold aisle, which drastically improves thermal routing in the rear of the rack and makes the ergonomic day-to-day management of these heavy, cable-dense systems much easier for the human operators.
It is a total paradigm shift from top to bottom. We have a revolutionary server drawing immense power. We have the liquid architecture capable of capturing 98% of that heat, driving down the power, space, and water footprints.
It all works in harmony.
But I have to bring us back to the harsh reality of the business world for a minute. Having an elegant design on a white paper, or even having the servers physically sitting in a warehouse, is largely meaningless if you can't get them powered on and crunching data.
The deployment phase is notoriously difficult.
Right. The history of data center construction is painfully, agonizingly slow. You have to secure land, pour concrete, negotiate massive utility contracts, run miles of bespoke piping, integrate software from a dozen different vendors, and pray it all boots up correctly.
It is a monumental undertaking.
So how does this highly complex liquid technology actually get deployed at scale in a world where AI companies are fighting a ruthless zero-sum war to be first to market?
The deployment bottleneck is precisely what Supermicro attempts to solve with the final major component detailed in the document. It is an initiative they call DCBBS, which stands for Data Center Building Block Solutions.
Building block solutions sounds like Legos for enterprise tech.
It is a fundamental shift away from the traditional, highly fragmented procurement model of IT infrastructure.
So historically, how did this usually work? A company would buy servers from vendor A, rack enclosures from vendor B, liquid cooling manifolds from vendor C, and management software from vendor D.
Exactly. And then they would hire a third-party systems integrator to try and force all these disparate pieces to talk to each other.
Which sounds like a logistical and engineering nightmare.
It is. Integration testing alone can take months. Because if there is a fluid pressure leak in a manifold, vendor C blames vendor D's rack alignment, while vendor A blames the software. It is constant finger-pointing.
Total gridlock. So how is DCBBS different?
DCBBS is an end-to-end vertically integrated solution. The source states that this single building block includes the servers, the racks, the networking fabric, the storage arrays, the internal piping, the management software, and even the ongoing maintenance service.
All from one place. So it is completely pre-engineered to interlock flawlessly on day one.
Exactly. The fluid dynamics are perfectly matched to the pump pressures natively. The software APIs natively understand the specific thermal telemetry of those B200 GPUs.
By removing the integration friction entirely, Supermicro vastly accelerates what the industry calls TTO, right? Time to online.
Yes. Time to online is the ultimate metric for CFOs right now. And the numbers here are what really catch the eye. The white paper asserts that utilizing this building block solution shortens the data center deployment process from a typical 12-month timeline down to just 3 months.
From a year down to a quarter.
Slashing 9 months off an infrastructure deployment schedule in the current technological climate is not just a logistical convenience. It is a profound strategic weapon.
I really want to analyze the opportunity cost here. Connect this for the listener. If you are the CEO of a major AI research firm or a hyperscale cloud provider, why does a 3-month deployment fundamentally alter your business trajectory compared to a 12-month deployment?
Because in the current AI arms race, compute is the ultimate currency, and hardware innovation cycles are moving at a breakneck pace.
A new chip comes out every year now, it feels like.
The generations of GPU architecture are literally overlapping at this point. If it takes you 12 months to build out a facility, integrate the hardware, and test the liquid loops, the cutting-edge silicon you purchased a year ago might literally be a generation behind by the time you finally flip the switch to begin training your model.
Oh, wow. You have spent billions of dollars in capital expenditure, and your brand new, pristine facility is technologically obsolete on its very first ribbon-cutting day.
Exactly. while your competitors, who deployed a pre-integrated solution much faster, have already trained their next-generation models on the same hardware and are moving on to the next architecture.
Time to online dictates time to market.
A 3-month deployment means you capture the absolute maximum value from the compute lifecycle of the hardware. You accelerate the training of your foundation models, you launch your enterprise API services 3 quarters ahead of schedule, and you begin generating massive revenue on that infrastructure investment almost immediately.
DCBBS bridges the gap between the incredibly complex physical engineering of liquid cooling and the brutal, unforgiving economic velocity required by the AI market.
It is the operational vehicle that delivers the physics.
It all forms this incredibly tight, interdependent loop. We started this deep dive looking at the raw, inescapable physics of heat transfer, analyzing exactly why forced air simply cannot keep up with the soaring TDPs and the massive current draw of parallel processing.
And then we decoded the new industrial math, exploring how the density and thermal capacity of liquid drives down those 4 crucial UEs.
Right, dropping PUE by saving 40% on power, dropping SUE by saving 60% on physical footprint.
And fundamentally challenging our assumptions about WUE by actually conserving 40% on water usage compared to those evaporative chillers.
Which all cascaded beautifully into a 20% reduction in total cost of ownership. Then we dug into the mechanical blueprint of the DLC-2 architecture itself.
Understanding how a 45-degree delta T allows hot ambient water to efficiently cool a 90-degree chip, and how those custom microchannel cold plates capture 98% of the thermal load across every single major component on the board.
We looked at the sheer density of the SYS422GS server, packing 8 1,000-watt GPUs into a 4U space, while simultaneously lowering the acoustic environment to a safe, quiet 50 decibels for the human workers.
And we grounded all of this incredible cutting-edge engineering in the harsh business reality of the AI gold rush, where deploying a pre-integrated building block solution in 3 months instead of 12 represents the difference between market dominance and total obsolescence.
It truly is a masterclass in how physical constraints force revolutionary engineering.
It is indeed. And as we conclude our analysis of this white paper today, I want to introduce a broader implication, something for you to mull over as you think about the future of this infrastructure moving forward.
Oh, I love a good thought experiment. Lay it on us.
Well, throughout this deep dive, we have treated heat entirely as a liability, a dangerous, toxic waste product that must be aggressively captured, mitigated, and rejected into the atmosphere.
Right, something to be destroyed or pushed away.
But if the DLC-2 architecture is successfully capturing 98% of this massive, multi-megawatt thermal energy directly into a closed loop of 45-degree water, that fluid is no longer just coolant.
What is it then?
It becomes a highly concentrated, incredibly valuable vessel of captured thermal energy.
Wait, I see where you are going with this.
What if the AI data center of the future isn't simply a place that consumes power to compute, but actively functions as a thermal engine for civil infrastructure?
Oh, wow.
Instead of sending thousands of gallons of hot water to a cooling tower to be wastefully dissipated into the sky, what if that massive thermal highway was piped next door?
District heating, taking the exact same closed water loop that just cooled a rack of 1,000-watt GPUs and routing it beneath the streets to a municipal heat exchanger.
Exactly.
Yeah.
45 degrees Celsius water is the exact temperature profile required for modern radiant floor heating in residential grids.
No way. That's a perfect match.
It is a perfect match. It could be used to heat entire city blocks during the winter, entirely offsetting the natural gas consumption of the neighborhood.
That is incredible.
Or it could be piped into massive industrial-scale indoor vertical farms, providing perfectly controlled thermal environments to grow food for urban centers year-round, completely powered by the byproduct of large language model training.
That is a staggering vision for the future, because the sheer electrical energy required to drive the AI revolution is immense, and it draws a lot of valid criticism right now.
It does. But if we can capture 98% of that energy in a liquid medium, the physical byproduct of our artificial intelligence could literally be used to grow our food and keep our homes warm.
It transforms the data center from an isolated, power-hungry black box into a symbiotic component of the municipal ecosystem. The liquid cooling architecture doesn't just solve the bottleneck of silicon, it potentially opens the door to an entirely new model of energy recycling.
It is a very hopeful way to look at the massive industrialization of AI.
That is a profound and fascinating thought to leave on. The invisible cloud has a very heavy, very hot physical anchor, but that heat might just be the engine for the future of our physical world. Thank you for joining us on this deep dive. Keep exploring, keep questioning the hidden infrastructure around you, and we will catch you next time.